Electromagnetic lab, electromagnetic induction lab, basic concept number 4, physics 124, SUNY Fredonia, Professor Alan Haungs, lecturer. Here we're going to kind of tie it all together, make it practical. So we're going to talk about in this part, this final part of the lab, so you'll understand the whole concept completely. We're going to talk about the transformer voltage law and the transformer current law. Just to reiterate what I said earlier, a transformer has 2 coils in it at least and a metal core. So this represents a coil on the primary side. That's where we send power in. And this represents a coil on the secondary side. And when we apply a voltage here, we get a voltage there. And we can use the voltage on this side to operate something. If the voltage is too high on this side, we can create what's called a step-down transformer. And what that is when you have a lot of windings, how many turns, each one of these represents a turn around the each one of those little bumps represents a turn around the core. See how there's multiple turns? That's what this is, the number of turns in the primary, the number of turns in the secondary, the voltage in the primary, the current in the primary, the current in the secondary, the voltage in the applied to the primary, the voltage that comes out of the secondary. Okay, so if we want to step down a voltage, we have many turns on the primary side, fewer on the secondary side. If we want to bring a voltage back up, this represents your power source. We have many turns on the secondary side and fewer on the primary side. That's called a step-up transformer because it steps the voltage up. This one steps the voltage down. The transformer law is very basic. There's a correlation between the ratio of the number of turns. So if I told you that a transformer is a step-up transformer, it takes 10 volts and steps it up to 100 volts, what would you know? You would know that there's a ratio here that equals 10, because you could just recalculate this out, move these variables around. Basically, just move the variables, you'll see it. In other words, this ratio, if it takes it down to 10, this would have to be 10 times less than that. This would form, 1/10. So this voltage times 1/10 would equal the output voltage. So that's a step down. So as long as you can figure out this ratio, and because when you talk about a transformer, you always talk about the input and the output voltage. So that's how you would first figure out the ratio, which is N1, the primary, that's the input side, and which is N2. Inversely, the current that's fed into the primary versus the current coming out is the exact opposite. So if we know N1 and N2, we're either doing this or this as a ratio. So in the same example I just said, so let's say if we wanted to step down the voltage, and so we're going to step it down to 1/10. That means we would have to step the current. We'd have to step the current down on the front end to get as much current on the front. You'd have 10 times as much current. You'd have 10 times as much current on the secondary available to the load. It would only take 1/10 of the current that it would normally have taken had it been a 1-to-1 ratio. With a ratio 1-to-1, whatever voltage is here, whatever current is here. But with the transformer and the current law, you can, by virtue of these ratios of how many turns are in this one versus that one, you can figure out the current that's reflected back to the secondary from the primary and vice versa. So why would you have a step down and a step up transformer? Well, when they make electricity at the power plant, they step it way up to hundreds over 100,000 volts. And why do they do that? Because that electricity has to travel a far distance. And voltage is what overcomes resistance. So you don't want wires and your overhanging wires that are 10 feet thick. You want them to be, a cable maybe an inch thick or something. So what you do is you have to lower the current. How do you lower the current? You have to raise the voltage, because current times voltage is power. But you can't bring 100,000 volts into your house. That would be too dangerous. So you have to step it down. So they step it down to 120 volts. So first so from the alternator at the power plant, they step it up, take it far distance. Then they take it to a substation, which then steps it down so that it can then travel along the roadways safely. It's not on those super high towers. And then it goes to a transformer somewhere near your house on a pole, telephone pole usually, and they step it down one more time to 120 volts and bring it into your house. So the purpose to have it stepped down is its safety, but the purpose of having it stepped up, the voltage, is to basically cause it to be more cost effective to transfer electricity for a far distance. So let me tie together the two thoughts previously. So we had Faraday's law of induction, and what he discovered was if you have a machine like this, a coil wrapped around a core, and they both share the same core, if you put current into this, a changing current will create an electric field. The electric field will oppose this applied voltage, and it will cause very little current to flow through here. That's called self-inductance. That same change in current will also induce a voltage, will induce that same electric field, will then also create a voltage in this wiring, and that direction of that voltage, if this were to supply current to something, would create a current, and that current would be in opposition, its change would be in opposition to this current. So the magnetic field in this core almost stays about the same. It goes up and down, up and down, up and down, but it doesn't go up and down real far when there's a high current being demanded here. It stays relatively up and down very consistently. So drawing a lot of current here does cause a lot more current to occur here, but the current that's coming from this side causes a counter magnetic field, so that in such a manner that it will reduce the magnetic field in this core, but it will be in such a manner that it will reduce the induced electric field, so there'll be more current coming in through here. So that's basically the combination of Faraday's law and Lenz's law, that one of them induces a current, that this induces a field, an electric field. It creates an electric field, and the electric field then induces a current on this side. So that's Faraday. But Lenz's refinement to Faraday's observation is that the responding direction of the field that's created by the changing magnetic field is such that it opposes the voltage coming in here, and also the current established here creates a counter-magnetic field that is resistive. It counteracts this magnetic field. That's the physics of it. But from the practical side, this is where if people can just master this is the most useful side of it. This is where it becomes applicable. That you can take a low voltage, take it into a high voltage, and then transfer it a long distance very efficiently, then bring it to the final destination, and then turn it back into a low voltage. And when it's a high voltage, it occupies very little current on the wire. So the wires can be relatively thin and not too expensive. You have big insulators on them, but small, thin wires. And then when you bring it into your house, you make the wires a little bit fatter, but you bring the voltage down to a safe level. So that's all of it in a nutshell. Let me just look at the questions, make sure that you're capable of answering the questions. So a uh, a changing magnetic field creates an electric field. The electric field, its magnitude is proportional to the rate of change of the magnetic field. Um, if something is conductive and it's exposed to a magnetic field, it will result in a flow of current, and that flow of current will create its own magnetic field that's trying to counteract the change of the magnetic field that's creating everything. A transformer works with the principle of uh, magnetic inductance, and the reason why we step voltages up and down is for safety's sake and for cost efficiency. You all have a really nice night. It's been a long day.